Hello and welcome to my poster session. This is Jiaqi Liu from University of California, San Diego. Today, I'm going to talk about particle configurations for branching Brownian motion with an inhomogeneous branching rate. First, let me introduce the model. Aiming to understand the evolution of population undergoing selections, Roberts and Schwensberg in their 2020 paper consider the following BBM with an inhomogeneous branching rate model. We begin with some configuration of particles on the real line at time 0. Each particle independently moves according to Brownian motion with strict negative rho. Each particle at the location y independently dies at rate 1 and undergoes diaxial branching at rate 1 plus beta y. Therefore, the difference between the birth rate and the death rate is equal to beta y. This model has its natural biological interpretation as a population model subject to natural selection. The question we are interested in is, what is entire particle configuration in the long run? To answer this question, let me introduce several assumptions. Because we are interested in the limiting behavior of the process, we need to consider a sequence of models indexed by n. We assume that the drift parameter rho is small, and the branching parameter beta is even smaller, such that the ratio of rho cubed and beta goes to infinity as n goes to infinity. These two parameters are closely related to the mutation rate and branching rate. These two parameters are tuned in a way such that the rate of beneficial mutation is large, but the selective advantage of each mutation is relatively small. We also need two more technical assumptions on the initial configuration of particles. Roberts and Schwensberg first answered our questions at the origin and the right edge. They analyzed particles' distributions at the origin and the right edge at time t of the order of rho over beta. They showed that at time tn, most particles are near the origin, and the empirical distribution of particles defined like this approaches to the standard normal distribution as n goes to infinity. Although the bulk of the distribution is Gaussian, the behavior near the right boundary L is different. They define a random measure which characterizes the empirical distribution of particles close to the right boundary L, and shows that this random measure converges in distribution to the probability measure mu with density proportional to the area function. Our work aims for the entire particle configuration from the left edge L dagger defined to be negative 5 rho squared over 8 beta to the right edge L star defined to be rho squared over 2 beta. Roughly speaking, most particles will stay in the interval from L dagger to L star. We are interested in the number of particles in a sequence of intervals in, satisfying the following three assumptions. The first one is the length of the interval goes to infinity as n goes to infinity. Second, if an is greater than 0, that is to say the whole interval falls in the positive real line, then the distance between the right edge and the left endpoint of the interval is a lot larger than beta to negative 1/3. The third restriction deals with the case when the interval falls in the negative real line. So we specifically add the last two requirements because the distribution of particles which are within distance beta to negative 1/3 of the right edge or the left edge are very different from the bulk of the distribution of particles. So we have to rule out these two cases. We define Zn having this form. We'll explain the meaning of Zn later on. Now we will be able to fully answer our questions. We want to answer the question regarding the entire particle configuration from the left edge to the right edge. We define two functions t of y and g of y having this form. Let n sub tn of in be the number of particles in the interval in at time tn. Our theorem shows that suppose all of the assumptions in the previous slides hold. If t minus t of z is of the order of rho over beta, then the number of particles in the interval I at time t over this expression converges to 1 in probability as n goes to infinity. So this theorem gives a description of the number of particles in any given interval in the long run. The randomness is characterized by this stochastic process z, which measures how the overall size of the process changes over time. The deterministic part has a density formula proportional to e to the g of y over square root 2 pi ty. The theorem also points out that particle configurations in the future time t, which is order rho over beta time after t of z, depends on the configuration at time t minus t of z. Next, I will explain the meaning of z and why the number of particles in AB depends on the configuration t of z time units in the past. Here, this value z is essentially the point where the density of the number of particles in AB is maximized. It was shown in the proof that the number of particles in any given interval AB is dominated by the number of particles that are close to z. Furthermore, if we consider the optimal path, the particles which ends up near z must follow to achieve the maximal almost sure growth rate. It will have this shape. The optimal path will follow the trajectory along the right edge up to time t minus t of z, and then drift towards z as a parabola. Therefore, most of the particles in the interval AB at time t are actually descendant of particles that are close to the right edge t of z time units in the past, which explains why the number of particles in AB depends on the configuration at time t minus t of z. That's all for my session, and thank you for your attention.